Hello everyone, I'm Asma. I'm currently pursuing my graduation in Information Technology from Gokaraju Rangaraju Institute of Engineering and Technology. I'm here to present our mini project which I have worked on along with my teammates Shalini, Ruchita and Gauri. Before I begin, I extend my heartfelt thanks to V. Akhila ma'am for her invaluable guidance and support throughout this project. Our project is titled Sign Language Recognition Using Deep Learning Algorithms, and it focuses on addressing the significant communication challenges faced by individuals who are deaf and mute. Often unfairly referred to as dumb and deaf, these individuals find that traditional methods like speaking and writing languages inaccessible, which makes it difficult for them to interact with the world. To tackle this issue, we have developed an application that leverages deep learning algorithms to recognize and interpret sign language. This technology aims to bridge the communication gap, providing a crucial tool for improving the ability to communicate and interact effectively. Before we dive into our solution, let's take a look at existing sign language recognition systems. Existing sign language recognition systems primarily identify individual alphabets and often fall short in recognizing full words and phrases. They struggle with accuracy in different lighting and backgrounds, require manual feature extraction, and face real time performance issues. Additionally, these systems lack flexibility, integration with other technologies, scalability, and robust security measures. They also provide minimal feedback to users for improving their signing techniques. Our project aims to address these limitations by offering a more advanced, functional, and adaptable solution for the deaf and hard of hearing community. This new system is designed to recognize entire words using deep learning techniques, particularly convolutional neural networks. This approach enhances accuracy, reliability, and real time performance by automating feature extraction and adapting to various sign languages and gestures. Our system also includes a user friendly interface, integrates seamlessly with other assistive technologies, and ensures strong security and privacy. Looking ahead, potential improvements could include recognizing complex sign language grammar, supporting multiple languages, and incorporating user feedback along with augmented reality technology. By tackling the current challenges and introducing new features, our system aims to greatly enhance communication for the deaf and hard of hearing community. Now let's take a closer look at the system architecture of our project. Here's how our system is structured. We start with the input source. This is typically a camera feed that captures the user's hand movements. Next, we have hand detection. The input is processed through a hand detection module called hand detector, which isolates and identifies the hand gestures. When the data is fed into a neural network model, we have used a pre-trained Keras model to process the detected hand gestures. Under the gesture classification, the neural network classifies these hand gestures into predefined categories. This is where deep learning algorithms come into play to interpret the gestures accurately. Recognized gestures are mapped to specific categories such as hurts, pain, and other common expressions through the category mapping process. This mapping allows the system to fully understand and interpret the complete gesture in the gesture recognition phase. The interpreted gesture is then translated into a result which can be communicated to the user. To ensure reliability, the system calculates the accuracy of the recognition process. Finally, users can control and stop the process using keyboard interrupts, providing an easy way to manage the system. This structured approach ensures efficient and accurate recognition of sign language, enhancing communication for the deaf. Next, let's dive into a class diagram which outlines the key components and their interactions within our system. The CV2 video capture class captures the video input which is then processed by the hand detector to identify hands in the frames. This processed data is sent to the classifier which uses the Keras model to load a pre-trained model and predict the corresponding sign language gestures. This streamlined interaction ensures efficient gesture recognition from video input to final prediction. The use case The use case diagram illustrates the interaction where the user starts the webcam to capture video. The system translates and recognizes gestures by extracting and matching features, then displays the results, providing real-time feedback. Coming towards the sequence diagram outlines the process where the user captures input via CV2 video capture. The hand detector processes the input frame to identify hands, which is then passed to the Keras model for loading and predicting gestures. The recognized gestures are finally classified and displayed to the user. Next, the activity diagram. The activity diagram depicts the process flow where the user performs hand gestures. The system extracts and matches features from these gestures, leading to gesture recognition. The recognized gesture is then translated into a result which is communicated back to the user. Following the activity diagram, I would like to discuss the following training process employed for our gesture recognition model. We utilized Teachable Machine, a user-friendly tool that facilitated the creation of our model. Through this platform, we were able to capture extensive image samples of various hand gestures using a webcam, which served as our training dataset. After training the model with these samples, we exported it into the Keras format. This step ensured that our model could be integrated smoothly into our system, providing accurate and real-time recognition of hand gestures. Without further delay, let's move on to the implementation phase of our gesture recognition system. We utilized a structured approach using Python, incorporating essential libraries such as CV2 for video capture, CVZone for hand tracking and classification, and Keras for loading a pre-trained model. The first step involved in importing the necessary libraries and initializing our hand detector and classifier with a pre-trained Keras model and its corresponding labels. Our categories included common gestures such as hurts, I love you, pain, stop. The core functionality of our system involves capturing video input from the webcam, detecting hands within the video frame, and classifying the detected hand gestures using a trained model. This process runs in a loop, continuously capturing and classifying gestures until interrupted by the user. Additionally, we implemented accuracy calculations and visualizations using confusion matrices and bar plots to evaluate the model's performance. This comprehensive implementation ensures that our system is capable of real-time gesture recognition with accurate and meaningful results. To run our real-time sign language detection project, we first activate the virtual environment by entering the command such as 1v/script/activate in the command prompt. After activating the environment, we execute the main script using python check.py. This script initializes the hand detector and classifier, captures video input, and continuously processes frames to predict and display sign language gestures in real time. The results, including the predicted gestures and its corresponding labels, are shown on the screen. Coming towards the execution part, as we can see, the camera prompt has opened. This gesture is for I love you, this is for pain, this gesture is for stop. As we can see, our sign language recognition system correctly identifying and displaying the stop gesture. The real-time prediction is shown as stop on the top left of the frame, indicating the system's accuracy in recognizing the specific gesture. This successful detection underscores the model's effectiveness in processing and classifying sign language gestures from webcam input, providing immediate feedback to the user. As we can see, the terminal output showcases the sign language recognition system's performance, displaying predictions and corresponding true labels for various gestures. The system consistently predicts gestures like I love you, hurt, pain accurately as reflected in the repeated correct matches. The overall model's accuracy is reported as 100%, indicating exceptional performance during testing and reliable gesture classification. The confusion matrix provides a detailed performance analysis of the sign language recognition model. It shows that the model accurately classified all instances of the hurt gesture I love you gesture, pain gesture, and stop gesture with no misclassifications. In summary, our sign language classification project utilizes deep learning and computer vision techniques to develop a real-time system capable of recognizing sign language gestures. By employing a pre-trained CNN, the system effectively processes webcam input to identify and categorize gestures, delivering instant feedback through an intuitive user interface. Looking ahead, potential improvements include broadening the range of recognized gestures, enhancing system performance, and refining user experience with more detailed feedback. Future developments could also involve adding multilingual support, integrating with assistive technologies, creating interactive training modules, and implementing robust security measures to increase the system's value for the deaf and hard of hearing community. Thank you.